Laura Lee, do you know what makes a cloud?
No.
You haven't had that in school?
No.
Well, I'll tell you what, I'll give you an explanation and you have to tell me whether it's correct or not.
Okay.
Okay? There's moisture in the air called humidity, okay? Floating around all over the place. When the air that has that moisture in it, it gets cool, it can't hold as much moisture anymore, so the little molecules of water come together to form a water droplet, and that's a cloud.
Right.
True? Do you think that's true?
True.
Sounds pretty reasonable. Okay, well, we'll sort of duplicate that same thing, and you'll see whether it's true or not. Here's a little water.
Okay.
Put it in that jug. That's going to be the moisture in the air, okay? I'll shake it up so we now have humidity. Now, instead of cooling it off, what I'm going to do is put the stopper in it like that, and at the other end is a pump that'll put pressure on it. That, in effect, heats up the air inside. Then when I release it like that, it's going to suddenly drop the temperature, and we should get the cloud, according to you, if you think what I said is true.
Right.
Okay, put on the safety glasses. It isn't very unlikely that anything could happen, but you never know, so we'll be prepared. All right, see, here's the pressure. Feel it? Okay, right there. Now, when I release it, you say there should be a cloud in there.
Yeah. There's no cloud.
No cloud. Here, you want to take the safety glasses off for me? Because my explanation was okay, except I left out one very important part. And that is, when the little pieces of moisture are floating around in the air, they won't condense into a little droplet unless there's something for them to condense on. Most of the time, it's dust particles in the air. Okay. This time, we're going to put dust particles in the jug. You light a match and throw it in there so we will get smoke particles in there.
Okay.
Then I'll put the, you put on your safety glasses then. Okay, now I'll put the pressure on. Now, if what I say is true, we should have a cloud, right?
Right.
Like that?
Wow.
Isn't that nice?
Yeah.
In fact, have you ever, now you can take the safety glasses off again. Did you ever hear of cloud seeding? Seeding
No.
the cloud? Well, you've heard of making rain.
Yeah.
Okay, when they make rain, it means that scientists have found that the moisture in the air up at the altitude has enough moisture to condense, but there's nothing for it to condense on.
Right.
So they go up in an airplane and they drop stuff for it to condense on,
Yeah.
usually iodine crystals or something. So now, what do you need to make a nice cloud?
Well, first you need water.
Water, vapor in the air.
And then you need dust particles.
Something, well, there's probably enough left right in there.
Yeah.
Watch. See how it disappears when I heat up the air with the pressure?
Yeah.
Okay, now watch.
Whoa.
Okay, now it's your turn to make a cloud. Here, you can take the safety glasses off. And back there is another jug. You want to bring that up?
Okay.
Okay, I would like you, Laura Lee, to make a cloud in this bottle. What do you need?
Okay, first I need some moisture.
All right. Moisture, okay, I'll shake it up a little bit. Then what do you need?
I need
Something formed to what?
something to condense.
Condense, okay. Okay, safety glasses. Hold it on. Nice and tight. Are you ready?
Yeah.
Make a cloud in the bottle. There you go. Very nice. Sharon, I'm mixing these water from these two pans to make sure that it's all the same temperature. And then I'm going to put them down side by side, and I want about the same amount of water in each one. Can you tell me a...
That looks pretty good,
Pretty good?
actually.
Oh, I'll be darned. Now, what I'm going to do is put them on those two burners that I've got burning up there, and one is going to have a lid on like that. Which one will boil first?
I think the one with the lid will.
Why?
Because the lid will trap in the heat.
Okay. That's partially true. The lid will trap in the hot molecules, which are the molecules that are moving faster, because when you add heat to water, you speed up the motion of the molecules, and when you get them to fly apart and become a gas, that's when you're boiling. In this case, we're losing some of the hot molecules. They're flying off into the air, like evaporation.
Right.
In this case, they're bouncing up on the top, condensing back into water, and then running down, and so we're conserving all the hot molecules. So keep an eye on them and see which one will win the boiling race. See any bubbles coming up?
Yeah, I can see a few.
Few?
Yeah. More than the open one.
I see one or two there. Oh, there, that goes.
Yeah.
See it?
Starting to boil
There, it's
now.
boiling already. And that one's going to start, but it isn't going as fast as that one. So you were absolutely right. The pot with the top won the boiling race. This 13-year-old boy fell through the thin ice on a lake in Minneapolis. Fortunately, as documented by KMSP-TV, he was rescued after 27 minutes in the very cold water. In spite of the extreme exposure, he suffered no permanent damage. Why? Scientific research at the University of Minnesota School of Medicine in Duluth provided an answer. The research is supported by the Sea Grant Program, the U.S. Navy, and a manufacturer of survival equipment. The danger comes when exposure to cold lowers the so-called core temperature of the brain, spinal cord, and lungs. The volunteer has been wired with sensors to measure the temperature at different areas. As his body senses the cold, it automatically protects the important core temperature by restricting the flow of blood to his arms and legs. Without this reaction, his core temperature would fall more quickly. The scientists make sure the volunteer comes out of the water before he's in any danger. They also run tests in Lake Superior, since exposure to very cold water can be the result of a boating accident. In this experiment, the subject will try to guess when his vital core temperature has fallen. After 10 minutes in the water, his core temperature has dropped significantly, but he doesn't realize it. After 16 minutes, his core temperature is dangerously low, so the team pulls him out. The scientist also tests survival equipment designed to provide better protection against the danger of exposure. No doubt the boy's body maintained his core temperature and thus avoided the harmful effects of exposure to the cold. Drip, drip, drip. You've seen a dripping faucet like that, haven't you? And sometimes people don't realize that it can be quite wasteful of water. So today you and I are going to figure out how much water it really wastes. Let's assume that it's dripping once a second.
Okay.
Okay? I'm going to shut it off because I don't like to waste water. Let's figure out how many drops there are in 1 cc. And see the 1 cc mark down there on the bottom?
Yeah.
Okay, now if you want to be a real scientist, you hold it up and you look right across so that you're seeing that line, and you count the number of drops
Okay.
that go until you make 1 cc.
1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26,
Right to the bottom of the
27.
27. Okay, remember that. 27 drops equal 1 cc. Now, if that drip continued for 1 whole month, it would be a certain volume of water. What's this one?
100 cc. 1 liter. 4 liters. 10 liters. And 20 liters.
Do you think it would be any of these volumes?
Well, there's 5 of them out here, and it wouldn't be the smallest. And it wouldn't be the biggest. It's too big.
Well, so you're just sort of taking a wild guess, really, right?
Yeah.
So which one are you going to guess?
I'd say 10 liters.
10 liters?
Yeah.
This one?
Yeah.
Okay, let's actually calculate it and see how close you came. Here's a pen. So here you can fill in how many drops for 1 cc?
27.
Okay. Okay, now we just assumed that it was 1 drip a second. So how many drips would be 1 cc? How many seconds?
27.
What, 27 seconds, right. Okay, now multiply it by, this was 1 cc, now multiply it by 100. How many seconds?
2,700.
Right. Okay, now we wanted to find it, that's seconds, now find minutes. What do you do? 2,700 here,
Okay.
divided by 60. I have my calculator all set for you. There it is, turned on,
2,700 divided by 60.
equals, what do you got?
45.
Okay, up here, 45 minutes. Okay, now what are we going to do? We're going to multiply by 10. So what do you do here?
45 times 10?
Right, just add a 0, right?
Yeah.
Okay. Okay, now we're going to take that figure. That's, by the way, 1 liter.
Okay.
Now we're going to find it, we're going to change it into hours. So what do you put here?
450.
50 divided by 60. Clear?
450 divided by 60 equals 7.5.
Okay, right here, 7.5 hours. Notice that's 1 liter.
Whoa.
Okay. Now, we're going to multiply that by
100.
100. So what do you put here?
750.
Okay. And 750 is 100. Now, we want to find out how long it's going to be. We were in what? We were in hours.
Okay.
And we want to find it by days. What do we have to do?
750 divided by 24.
Right? 700, well, write it in there first, right? Okay. 750
150 divided by 24.
equals. What do you got?
31.25.
31.25 days is about a month, right?
Yeah.
How many cc's? 100
100
liters.
liters.
Yes, you said what? You thought 10? Do you realize how many liter bottles that is? 100? In fact, in 1 month, at 1 per second, here's how much water you'd waste. Come on, I'll show you.
Wow.
Yeah. Now, how many did you guess?
Just 10 liters. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10.
And how many liters in a month?
100 liters.
Yeah, dripping in 1 a second. And notice I have every 10th bottle moved out. So there's 10, 20.
30, 40, 50, 60, 70, 80, 90, 100.
Right. And if that happened to be hot water that was dripping.
You'd waste a lot of energy.
Right. So conclusion?
Get rid of all drips.
Right. You can put that one in any old way because you'll see why later. It really doesn't have to stand up. But this one, I'd like you to put in straight up because you're going to light it.
Okay.
Okay. Very good. Now, put that lighted candle in that jar.
Okay.
Okay. Now you can put the top on that one.
Okay.
Now we have 2 jars exactly alike, or at least as close as you can get them. Both have candles in. That one's burning, this one's not, right?
Yes.
You've heard about a control when you do a scientific experiment.
Yes.
What's the purpose of the control?
Well, so you can compare the, your experiment to nothing that's happened
Right,
to
yeah.
one.
In this case, even though it's laying over on the side, nothing is happening in this one. While that one, oh, the fire went out. Now, I'll shake this one, you shake that one.
Okay.
What we want to try to do is to mix the gases in the jar with the liquid.
It's turning kind of a different color.
Yeah. That's because the blue is from a chemical called bromothymol blue and is a test for a certain chemical. Here, put it down. What do you suspect made the change?
Well, I think the carbon dioxide from the candle's flame made the difference.
Made the change, because that's the only
Yes.
difference. This one was lighted, that wasn't, right?
Yes.
That's right. This is a test. Bromothymol blue changes color in the presence of carbon dioxide. Okay. Now, so that you should be able to predict what's going to happen over here, you're going to blow through that one, and I'm
Okay.
going to pump air through this one. What should happen?
Well, I think that because I'm blowing through this one, it should turn a different color because I'm letting out carbon dioxide.
Sure. When you breathe in, you breathe in
Yes.
oxygen, you give out carbon dioxide. Okay, I'll pump air, and you blow in carbon dioxide. What's happening?
This one turned a different color,
Yeah.
kind of greenish.
Proving again the presence of what?
Carbon dioxide.
Carbon dioxide, right. Now I'd like you to meet some friends of mine that you have a lot in common with.
Okay. Oh, those are mealworms.
Yes, mealworms. And when I started out, that solution down there was blue. So what must the mealworms do?
They would probably let out carbon dioxide
Right.
to make this color.
You don't ordinarily think of worms taking in oxygen and
No.
giving out carbon dioxide,
No, you
but they
don't.
obviously do because they change color.
Yes.
So you want to put the mealworms back? Okay, good.
What are you going to do with the mealworms?
What, you want to go fishing?
No, I was wondering if I could show them to my class. This has been a really interesting experiment.
Well, okay, if you're going to do the mealworms, then you should do the bromothymol blue, too.
Yes.
Okay, here's a supply of that.
Okay,
So remember
thank you.
now what to do. Just make sure in every case that you have what is known as a control.
Yes.
And you can use bromothymol blue to test for the presence of carbon dioxide. Good luck.
Thank you.
In all your years at school, you'll probably never be in a classroom like this one at Mammoth Cave National Park in Kentucky. Every summer, Dr. Patty Jo Watson of Washington University in St. Louis conducts a class in cave archaeology, sponsored by Western Kentucky University. She introduces her students to the procedures they will follow and explains the safety rules. Because exploring a cave can be dirty work, some of the students suit up in coveralls. They have to be in good physical shape since the sessions last from 4 to 12 hours each day. Dr. Watson's specialty is studying how early Indians used caves. At various places, she points out the artifacts that can be found. This piece of cane was used by prehistoric Indians as a torch. And here's a fragment of a bowl made from a gourd. The students learn that the prehistoric Indians used Mammoth Cave for shelter and to collect flint and minerals. The stable humidity and constant temperature year-round have preserved many artifacts. Since this is a national park, none of the articles can be removed, so another class can examine them in their natural surroundings. The students can't become cave archaeologists in a week-long course, but can learn respect for the artifacts they may encounter when they explore other caves on their own. Who knows? Perhaps someday you'll find yourself in an unusual science class like this one in a cave. Verse that's obviously now full, right?
Yes.
I want you to do the same thing with this bottle over here.
Okay.
I put a little food coloring in there so you can see it better because we are going to do an experiment that I like to call the mysterious elliptical bottle. Keep going till it comes out so we were sure it's absolutely full. Keep going. Go. There we go. Okay. 2 bottles full of red liquid. What'll happen if you squeeze this round one?
It will overflow.
Okay, try it. Sure enough. Okay. Now, what will happen if you squeeze this one on the side? Try it.
It
Nothing
sinks.
coming out.
No, it goes down.
Why?
I'm not sure.
Well, now think. You know how to find the volume of something? Have you had
Yeah.
that in school? How do you find the volume of a thing like this?
Area times height.
Yeah, area of the
Oh,
base
yeah, base.
times the height.
Height.
Okay. Well, the area of this base is like a circle, right?
Right.
Okay. But notice the area of this base is not a circle. It's a thing called an ellipse. And an ellipse is like taking this circle and squeezing it so that it's like that. And notice that while this is the same circumference, the more elliptical I make it, in other words, the skinnier, watch what happens to the volume.
So it goes skinnier.
It's
kind of.
skinnier and skinnier, yeah. So pretty soon it would
It's
be
a
nothing.
line, right?
Right. So therefore, when you have an elliptical bottle, what are you going to do when you squeeze it?
It will go like,
Well, it's going to make it more like this one, right?
yeah.
Okay. You can see now why I call it the mysterious elliptical bottle because fill it full all the way. Okay, now squeeze it. Watch. Look how much I can add. A lot. Okay, now let it go. You see why I call it the mysterious elliptical bottle? Okay, great. This is how March marigolds look to you. But according to Dr. Tom Eisner of Cornell University, to an insect, they probably look like this. The flowers give off ultraviolet light, which we can't see, but which insects can. To attract insects to help spread pollen, plants develop flowers with ultraviolet patterns that are visible only to insects. Bjorn, you want to check my addition here? You know how to add up those columns?
Okay.
See if I'm correct.
3 plus 4 is 7.
Right.
7 plus 5 is 12.
Okay.
Carry the 1.
1.
1 plus 9 is 10. 10 plus 2 is 12. Carry the 1 again. 1 plus 1 is 2. 2 plus 3 is 5.
Okay, so that was correct.
Yeah.
Now, however, you're very good at math, but are you good at codes? Because that's what that really is. It's not a math problem. It's a secret code.
Oh boy.
And you said you were pretty good, so I thought I'd check you on it. In fact, this number is not important that it's 123, but any number from 120 to 129. And then look at 120. What is that secret code over there? 120?
Would be M.
Right.
Okay.
Okay, what's the, you can do these two together, right?
Okay. 42 and 47.
What is that?
They're both an E, I guess.
Right.
And 190 would be a T.
Mm-hmm. Okay, that's that one. Now how about this one? What's 3?
3 would be an A.
Mm-hmm. Next.
194 would be 190.
Mm-hmm. At. There comes a tricky one.
Oh boy. 325 here would be 7.
Right. So far we have what?
Meet at 7. Okay. 194 be T. 147 would be an O. 131 would be an N. 86 would be an I. I could probably guess from here.
Okay, what are the rest? G,
H.
H,
T.
T. So you see the idea of this secret code? Sometimes people, when they do substitution codes like this, they think that 123 is important, but it isn't. Only the first two numbers, as though there's a 0 behind it. You can ignore these, and the whole addition idea is just subterfuge. That's not important at all. Okay, you want to meet tonight at 7?
Sure.
Great.